we go. Okay, so I'm going to set the scene and talk to you a little bit about the classical scientific view of determinism. So determinism is the view that if we know the initial conditions to our system and we know all the laws that govern the system, then we should be able to predict its future perfectly, right? So if we want to predict any event, we should be able to if we know all the laws and the theorems that determine it. So this really took off in the 1600s when Newton came up with his laws of motion and universal gravitation. And the idea here was, well, using his laws, if we're able to predict the motion of an apple falling off of a tree, then we should be able to predict the entire universe knowing all of its laws. So I think if you study physics for any period of time, this is the most natural thinking to come away with, because as physicists, we just want to be able to explain everything. And even if we can't explain it today, we want to know that we're able to explain it. And with this thinking, we're able to do that. But, of course, there's loads of things in our society, systems that seem unpredictable, right? So weather forecasts. We can't seem to be able to predict weather 7 to 10 days in advance. Even with our supercomputers and the best satellites in the atmosphere, right, we still haven't improved at predicting weather. And the stock market, well, if we were able to predict the share price in the future, then we'd all be billionaires. And in economies, the economy seems like totally unpredictable the majority of the time. And even with all of our historical data and economic knowledge, we're not able to predict recessions. We see this coming up in nature a lot as well, with animal populations rising and falling in mysterious ways that just seem totally unpredictable. So this is where our chaos theory comes into place. So chaos theory was first coined by this man, Edward Lorenz. He's a mathematician and meteorologist in the 1960s, and he was trying to simulate the Earth's atmosphere and improve weather predictions. So he came up with a set of 12 equations and 12 variables. So these variables included things like humidity, pressure, temperature, all went into the equations. So it's a completely deterministic model. And one day, he went to rerun some simulations. When he inputted the numbers, he rounded them to 1,000th decimal. So this is a very small change, and he expected his results to be more or not aligned with the previous ones. But what happened was, when he reran the simulations, the forecasts were very similar for the first few days, but then they started to diverge from each other, and they diverged very quickly. And by day 10 or 15, the weather forecast was completely different. So this looks quite random and chaotic to a meteorologist who wants a concrete idea of what the weather is going to be in the future. And if we think of our deterministic view, then the weather should be something that we're able to predict, right? We have all the historical data, we have all of the knowledge, but we still can't seem to predict it accurately more than 10 days in advance. And what Lorenz found here is not that the weather isn't unpredictable, but that the system is so complex that it's so sensitive to the initial conditions that you give it. So he wrote a paper on this, and he called it, "Does the flap of a butterfly's wing in Brazil set off a tornado in Texas?" Now, some of you may have heard this saying before, and it's a metaphor, right? For can something so small, like the flap of a butterfly's wing, have this chain reaction that sets off a course of events and have exponential consequences in the future? So next I'm going to show you a simulation of the Lorenz attractor. So when Edward Lorenz was trying to simulate the convection, atmospheric convection, so this is the movement of air within the Earth's atmosphere, he came up with a set of equations, right? A deterministic model. But what we see now is that this system is very sensitive to the initial conditions that you give it. So I'm starting this simulation off with 3 points starting almost identically together. So as you can see, there's 3 points here, but they're so close together it just looks like there's one, right? And as time moves on, these points are going to start to diverge from one another, as you can see now. And then soon enough, these 3 points are going to be on completely different paths and have completely different endpoints. So the idea here is not that this system is random, because it's completely deterministic, right? It's just a set of equations, we're giving its input values, but it's so sensitive to those input values that it's just so hard to predict where our endpoints are going to be. So from this attractor, because it looks kind of like a butterfly, and his saying is title of his paper, the butterfly effect phrase was coined, and this became a really big thing through social media, but it's kind of the idea of how tiny changes can trigger these exponential consequences. And the important thing here is not that the tiny change is big enough or powerful enough on its own to cause these events, but that it sets off this chain reaction that influences everything around it. And in these systems, they're so interconnected that one small change affects everything and can build up to these exponential consequences. And I think we probably all have like tiny decisions that we've made within our life that have reshaped our entire life. You know, things like if we didn't apply for that job, or we didn't go to that party and met our best friend, all of these tiny decisions that we think are so small in the moment can have exponential consequences on our entire life. And I think what's really fascinating about the butterfly effect is that it makes us rethink of these big events, because we think big events and big times come from small or big causes, right? But the butterfly effect is contradicting that. It's saying you only need a tiny change to trigger these big events. A bit of an extreme example would be COVID-19, right? This started from one person in one city contracting a virus from an animal, and soon hundreds had the disease, and then thousands, and soon it spread across the entire world, right? And this resulted in our global lockdowns, millions of deaths, and social and economic effects that are still lasting to this day, right? And that just started from one singular thing that happened. So I'm going to go through a few more examples. So one of them is in space. What if Jupiter didn't exist? So during the early days of the solar system, Earth was being constantly bombarded with asteroids and comets. And Jupiter is this massive planet, 318 times the size of Earth. So that is a 2-scale drawing, and it's kind of hard to comprehend the actual size of Jupiter. But because of its size and gravitational pull, it absorbed all of these comets and asteroids that were heading to Earth, and it either took the hit or flung them out of the solar system. And because of that, Earth had a chance to survive, and life on Earth probably wouldn't have had a chance to, build or thrive. Even if Jupiter was a small bit smaller or a little bit further away from Earth, probably wouldn't have had the same effect, and life probably wouldn't have been possible. This also happens in nature a lot. So in the last few years, the sea temperatures rose by 1 degree. And this 1 degree temperature led to coral bleaching, which resulted in a lot of fish losing their habitats. And this has a knock-on effect with the livelihoods of fishermen in the area and towns that relied on the fish for a source of food. The good thing here is, though, that it's completely reversible. So if we get the sea temperatures back down, coral bleaching, completely reversible, and hopefully the fish population can regrow. But it's just an example, because even if we think about what led to that 1 degree increase in temperature, right? There was a million different decisions that a million different people made that would have led to that one thing happening, which then has all these knock-on effects. In economics, the 2008 financial crash, this started with the Lehman Brothers filing for bankruptcy. After that, a lot of the banks in the US were afraid to lend to each other. It caused a freeze in the credit markets. Businesses couldn't get loans, they struggled, there was unemployment rates went up, people couldn't get mortgages for homes, and then this didn't stop in the US, this spread across the entire world. And soon, one bank falling meant that there was an entire financial catastrophe. So, all these events and parts of these events can seem random, but they all came from somewhere. They were all caused by something, so are they random? And then the next question is anything truly random, right? So I take a simple example, like I flip a coin. You think it's a 50-50 chance, right? Heads or tails. But if you apply our deterministic view, right, if I know the angle that I flip the coin at, if I know the movement of all the particles around the coin, the force that I apply to the coin, all the initial conditions that go into flipping this coin, I could tell you exactly whether it's going to land heads or tails. So it's not really random at all, right? I think the main point I'm trying to get across about this is that things that we see as chaotic and random in society aren't truly random, but they're just so complex and so sensitive that they're very hard for us to predict, but they are purely deterministic. Another thing that can shape how we view randomness is human bias, right? Humans are biased and we have patterns. Like I ask you to pick a number between 1 and 10. Statistically, very few people will pick 1 or 10. And most people pick like a number in the middle or 7, which is the most common number. But if like statistically not every number is picked the same, then it's not really random at all. Also, how we view randomness can be very incorrect from our brains, right? If I flip a coin 5 times and I tell you I get heads every single time, people often think that this doesn't seem like a random combination, or the coin might be biased, or it might have been just lucky that we got 5 in a row. But in reality, this is just as random as any other combination. If I got heads, tails, tails, heads, tails, that seems like a more random combination, but it's got the same probability as occurring as 5 heads in a row. So a lot of what we think is random or looks random is just maybe shaped by human bias. So before I finish, I want to come back to this deterministic view, because from a mathematical perspective, it's quite concrete, right? If we have our initial conditions to a system, we know all the laws that govern the system. I mean, it makes sense that we should be able to predict its future. But from a philosophical perspective, it's very, very controversial. Because if you remember that determinism is the idea that our decisions that we're making are caused by something that's beyond our control. So if our decisions are all predetermined, and if they can be predicted, then are they really our decisions at all? And then philosophers will argue, like, do we have free will? And this leads you down a very dark rabbit hole, but, it's the whole idea of moral responsibility. And if our decisions aren't our decisions, then can we be held responsible? Can we be praised? Can we be blamed for them? And it's something you might want to think too hard about, or it'll keep you up at night. But that's it from me.
Thank you very much, Roisin. That was excellent. William, I know you said that our brains are elastic and